Hello, today we're going to solve an integral using a technique we've seen before on the channel. I guess if you've seen most of my videos, you'll probably recognize where this is going pretty soon. Oh, and by the way, you could easily solve this just by finding its antiderivative and evaluating it using a limit as x goes to infinity or whatever. And it's not difficult at all. The limits aren't too tough either, and I might do a video using that technique as well, but I think it's more interesting to see this nice example of a trick you can use oftentimes. So let's see, where do we start? First of all, we've got this 1 plus e to the power of ax, and that kind of looks like a geometric series, so let's just see what I mean by that. If we take the Taylor series for 1 over 1 minus x, that would be the sum from n equals 0 up to infinity of x to the power of n. Now note that this only works for x or the absolute value of x being smaller than 1, right? So otherwise this doesn't converge at all. So again, we've got this kind of similar stuff going on here. We've got a plus instead of a minus, and of course e to the power of x on the interval from 0 to infinity doesn't converge at all either. So maybe what could we do to fix that? Well, and this is a trick that is actually quite useful in a lot of these cases. I've solved, I think, 2 or 3 other integrals on my channel using a similar trick, and it goes as follows. So we're going to multiply the denominator and numerator by e to the power of minus ax. And by doing this, we're going to get our integral in a form that can make use of this Taylor series. So e to the power of minus ax, that means 1 times that is just going to give us e to the power of minus ax. And then these powers are going to cancel and going to give us e to the power of 0, which is 1 dx. So now our function e to the power of minus ax does actually converge on this interval from 0 to infinity, so we can make use of this Taylor series. So what if instead of x we were to use minus e to the power of minus ax? Well, that would give us 1 over 1 minus e to the power of minus ax. That would be equal to the sum from n equals 0 up to infinity of minus e to the power of minus ax to the power of n, right? Now notice that that is actually exactly what we need for this integral. First of all, these two minus signs are going to cancel. We're going to get a plus sign, which is what we have on the bottom of our integral there. Okay, nice. So we can use this result and we'll get the following integral from 0 to infinity of e to the power of minus ax, and then we're going to replace our 1 over 1 plus e to the power of minus ax with our identity here. So that would be the sum from n equals 0 up to infinity of minus 1 to the power of n times e to the power of minus axn dx. So now what we'll do is we'll switch the sum and the integral, and we'll just consider it as term by term integration, which isn't always allowed, but we'll do it here. So next up, what are we going to get? The sum from n equals 0 up to infinity of minus 1 to the power of n times the integral from 0 to infinity of e to the power of minus ax times e to the power of minus axn dx. And now we can see that we've just got a basic integral to solve. Let's just bring these two powers of e together. So we'll get the integral from 0 to infinity of e to the power of minus ax times n plus 1, and we can solve this integral easily. So we can immediately solve and get the sum from n equals 0 up to infinity of minus 1 to the power of n times, and then we've got this evaluation here, which is going to be e to the power of minus ax n plus 1 divided by minus a times n plus 1, evaluated from 0 up to infinity. Right. Now notice that we have to take a limit when x approaches infinity, and that's going to give us 0 immediately. And also, maybe I should have noted that before, but a has to be a positive number, otherwise this doesn't converge. And then the second thing to consider is what happens when x is equal to 0. Well, that exponent is completely going to be equal to 0, which gives us 1. So in the end, we'll have the sum from n equals 0 up to infinity of minus 1 to the power of n divided by minus a times n plus 1. Sorry, not minus, we're evaluating, so we're going to have a plus there. And now at this point, maybe first of all we can take this 1 over a out. We can use the same Taylor series from before. So I said 1 over 1 minus x was equal to the sum from n equals 0 up to infinity of x to the power of n. So we used that, we plugged some of the other things in, and we were able to convert this integral. Now, how can we use it in this case? We're going to integrate it. So this means if we integrate both sides, find the antiderivative, we can see that the log of 1 minus x, sorry, the negative log, should be equal to the sum from n equals 0 up to infinity of x to the power of n plus 1 divided by n plus 1. And luckily, this looks a lot like what we actually have there. So maybe we can plug some values for x in to get what we need. And indeed we can. So we just view this as a function and we plug in minus 1. So that's mostly inspired by the fact that we've got minus 1 to the power of n. So if we were to plug in minus 1 for x, that would work quite well. So this means that minus the log of 2, so 1 minus minus 1, would be equal to the sum from n equals 0 up to infinity of minus 1 to the minus plus 1 power divided by n plus 1. So minus the log of 2 would be equal to the sum from n equals 0 up to infinity of minus 1 to the n plus first power divided by n plus 1. And now we can take a minus 1 from both sides. So in this case, this plus first power is 1 minus sign, and that minus sign on the left side can also be cancelled. So in the end, we've got this equation for our formula here, and so in the end we get the log of 2 divided by a. So maybe let's rewrite our result one more time. So the integral from 0 to infinity of 1 over 1 plus e to the power of ax dx is equal to log of 2 divided by a. So a nice final result. Pretty simple, and I think this trick is really a must-know for a lot of integrals involving these exponential functions in the denominator. And of course, if you like this video, definitely let me know. If you've got any tips, also let me know. Thank you so much for watching. Until next time.